In this video, we're proving Euler's famous formula, e to the I pi plus 1 equals 0. So this is going to use a bit of calculus and Taylor series. So I'm going to assume some knowledge of Taylor series. So a Taylor series, I'm going to write a Maclaurin series, which is a special case of Taylor series centered at 0, is given by the sum from n equals 0 to infinity, the nth derivative of the function at 0 over n factorial, x to the n. So that's the Maclaurin series, and it looks complicated, but basically to find this coefficient of x to the n, you just have to take derivatives. So sine x, the first derivative of sine x is sine x dx is just cosine x. Then we have negative sine x, and it just cycles. So it turns out the Maclaurin series is actually pretty simple for that one. So I'm just going to write the Maclaurin series. I won't prove it. We'll prove it in a different video if need be. But sine x's Maclaurin series gives you that it's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and it just follows like that, alternating signs back and forth, positive, negative, doing odd exponents. And cosine x is the opposite. It starts at 1, and then it goes on to do minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And this 1 is really x to the 0 over 0 factorial. So let's keep those in mind. Now what we're going to do is we're going to try to prove. We're going to go ahead and set out to prove the theorem. So e to the x is another one we can do, and that's going to be it's 1 plus x to the 1 over 1 factorial plus x squared over 2 factorial plus so on x to the n over n factorial. So we're going to use that fact. Now we want to do e to the I pi. So we're going to plug in I pi for every x. So it's going to be 1 plus I pi over 1 factorial plus I pi squared over 2 factorial plus I pi cubed over 3 factorial, and it's going to go on like that. But I has a special property, as we know. We know that I equals I squared equals negative 1, I cubed equals negative I, and I to the 4th equals 1. So we're going to have to exploit that property in order to rearrange our function a little bit. So it turns out what we'll do next is we're going to go ahead and try to fit this to cosine and sine. So first we're going to change this a little bit. So I pi over 1 factorial is fine, but I pi squared, that gives you I squared, which because make this negative, and this I will vanish, and we'll have pi squared here. And then this I cubed will give you negative I, so we're going to put negative I pi cubed here, and we'll just follow like that. And I'll put one more term so we can see one more term. So this is going to be, the next term would have been I to the 4th, so that's going to give you 1, so it's going to be pi to the 4th over 4 factorial. So we have 4 terms to work with here, and we have a complete cycle within these 4 terms. Now what we're going to do is we're going to see cosine of x plus I sine of x. We're going to look at that function, which is often written as cis x in a closed form, short form. So let's look at that, and let's put this result aside for just a second. So we're going to remember that it's this, and we'll come back to that. So cosine x plus I sine x. Let's revisit cosine x's Maclaurin series. So that, as we knew, was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus minus x to the 6th over 6 factorial, and so on. So that's like that. And then I sine x is just I times every term in the Maclaurin series for sine. So it's going to be x I minus I x cubed over 3 factorial plus I x to the 5th over 5 factorial, and it's going to continue like that. And if we add them together, we're going to get 1 plus xi minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the 4th over 4 factorial, and like that. So every odd term has an I, every even term doesn't have an I, and they still alternate. So now what we're going to do that, and is we're going to compare that. We're going to go ahead and plug in pi into here. So instead of cosine x, we're going to make this specific. We're going to plug in a pi into all of this. So we're going to find cis of pi. So putting pi into here, we just get pi. Putting pi into here, we get pi squared. Then here we get pi cubed. It's all pretty standard. Here we get pi to the fourth. And now let's compare this with what we had found earlier. So using our e to the x, when we put e to the I pi, what we got, I'll put it in a different color, I'll put it in black. We got that we had 1 plus pi I over 1 minus pi squared over 2 factorial. And then we had minus I pi cubed over 3 factorial plus pi to the fourth over 4 factorial. And basically we had the same stuff because it's 1, this pi I, this minus pi squared over 2 factorial minus pi cubed over 3 factorial plus pi to the fourth over 4 factorial. And I think I have mentioned that these still alternate. They do not actually still alternate. They have a different pattern. Some are consecutive, some are not. So sorry about that. But the point is that we arrived at the same result in two ways. This result was arrived by doing e to the I pi. This result was arrived by doing cosine of pi plus I sine pi. So that gives you the equivalence that we are actually looking for. We can say that cosine of pi plus I sine of pi equals e to the I pi. But this does not look like we're done yet. So cosine of pi, we know, is negative 1. Sine of pi, we know, is 0. So this is all gone. So we know that e to the I pi equals negative 1, or e to the I pi plus 1 equals 0. We have proven it. Now, this is a pretty rudimentary proof because we have to assume a bunch of stuff. In a following proof, we will do a more elegant type proof.